Okay, fine-grained clastic rocks. These are always associated with the erosion and weathering of feldspar. Now, feldspar breaks down into solute load, but also into clay flakes, which we can't see with the naked eye. But under an electron microscope, as you can see here, you can see the individual flakes of of clay, which often group together. But on this side view here, you can see how thin they actually get. That's because of the atomic structure of feldspar itself. But they often group together as clay particles, forming the fine-grained sedimentary clastic rocks. So the two we'll look at are shale and mudstone. So this is where those clay flakes you saw on the previous slide group together. Now, shale is laid down in little laminations, in little layers associated normally with flood events, but also in deep sea conditions as well. And mudstone is random. Now, here is that shale. You can see very clearly the individual layers, what we call laminations. And when it breaks down, when shale breaks down into these little layers, we can also describe it as fissile. The grey colour is often associated with deep sea conditions because there's often a degree of carbonaceous. That means organic remains within the shale itself. Hence the fact that shale rock is often very good for oil and gas deposits. And finally, mudstones. Mudstones are associated with low energy environments such as river estuaries or marine harbours. Remember, that will be made of those tiny clay flakes which you can't see. There's no laminations. They're not laid down in those layers. The individual clay particles have been squashed and the water content has been reduced. And finally, it feels smooth when rubbed on the teeth because there's an absence of quartz. So here are a few past paper questions that we can work on. This is from 2018. For each of these questions, give yourself a bit of time to look at the question. Don't just jump straight to the answer. So this shows a field sketch of the hot desert. It's important to note that. And there are 4 different landforms: scree, a dried up lake bed, an alluvial fan, and a dune field. So we have to describe one weathering process responsible for the formation of scree in figure 5a. Now, immediately when we think of scree, we think of freeze-thaw weathering. But of course, this is the desert. So what's the other process, the other physical weathering process that breaks down rock to form scree? In hot deserts, that would be exfoliation. So what is exfoliation? So in hot desert conditions, the diurnal range of temperature is high, from hot during the day to freezing cold at night. This causes the outer layers, the external layers of rock, to expand and contract rapidly, and cause them to disintegrate and break off, which forms the scree. Okay, so here we see the sediment, a picture of some sediment typical of one of the landforms. So describe the texture shown by the sediment in figure 5b. This should be an easy answer for us. Let's go through it logically. We can talk about the degree of sorting, the size and the shape of the clasts. So, first of all, coarse clastic rock with some clasts over 8 centimetres in length. Quite easy to see there. Don't forget to quantify your answer. 8 centimetres in length. Make sure you quantify all your answers. Angular clasts with a long axis randomly orientated. The long axis is the longest part of the stone. If they're all in the same direction, that often indicates some sort of paleocurrent. But in fact, they're all different angles. Poorly sorted and texturally immature. So you can see they're all different sizes there. So we can call that poorly sorted, which is an indicator of the sediment being texturally immature. Remember, that means transported over a short distance. And finally, it is matrix supported. You can clearly see that the larger clasts don't really touch each other, but the fine bits of mud between them are supporting the weight of the structure. So where has this come from? The sediment is a characteristic sample taken from one of the landforms. Identify the landform and give 2 reasons to support your answer. Well, initially you think, oh, a large class, it could be scree. But really, because we have the muddy matrix in between, that can't be scree, because that would be large clasts touching each other. So it has to be transported over a short distance. So the most likely candidate there is this alluvial fan. Why is that? Well, the angular class indicates a very short transportational distance, and it's matrix reporting indicating rapid deposition. So alluvial fans are basically one-offs after flash floods where all the material is carried down at once and they're rapidly deposited. We can also show that because it's poorly sorted, it shows a short transportational history. And the exam board also says the whole variety of minerals showing short transportational history as well. So make sure you get any of those two in the answer. Now these questions are difficult. They require quite a lot of thought in planning them out. So the question says, sedimentary grains are transported by both wind and water in the hot desert environment. Assess the relative effectiveness of wind and water in the sorting and rounding of these transported grains. Give reasons to support your answer. So it's basically asking you about the processes of transportation in the hot desert area by both wind and water. So let's start with wind. So both wind and water transport grains within the desert. However, the wind would be more regular transporter as rainfall and subsequent river flow only occur in dramatic events, flash floods. So wind is constantly operating day to day, blowing the grains around, whereas flash flooding happens perhaps once or twice a year in desert areas, sometimes even more irregular, once every 10 years. But when they do come, they are very dramatic. So desert winds only transport lighter grains of sand. They're selective in what they transport. The process of attrition causes individual grains to smash into each other, rounding them off. Evidence of this can be seen in the pitted appearance of individual grains. From the desert sandstone in the last video, it shows those little indents, those pits, caused by the impact of other grains. So let's talk about water now. While water is rare in deserts, dramatic floods can occur once or twice per year. The energy of the floodwater can transport all size sediments, including large boulders, over long distances. However, these flash floods stop quickly and deposits materials in an unsorted way. So, this is the mark scheme. This is how you'd get 5 to 6 marks. This is directly from the mark scheme. Read through that and see what you think of the answer. They also put in the mark scheme what we call indicative content. So this is from the mark scheme as well. It talks about this is what you need to talk about for wind, and this is what you need to talk about for water. Pause the video and read through and make sure we've covered enough for our 6 marks. Okay, this next question is from 2011. Take a bit of time to look at the different sandstones, see immediately what you think they are going to be, what are the key things they show on there, and also don't forget, always check the size. Sometimes these are different, some people fall for that. Also it's a little trick, but people get confused by that. Lots of feldspar in this one, that should give you some sort of indicator. This is mainly quartz. Straight away you should be thinking, I know what that type of sandstone is. Okay, describe the texture of sandstone G shown in figure 3a. So this is from the mark scheme. Again, you should be familiar with these questions. It's clastic, fragmental, it's sub-rounded, rounded, it's 0.3 to 1.5 millimeters, medium grain size, and it's reasonably well sorted. So make sure you get those points in. Again, I'll say again, make sure you quantify your answers. Sandstone G is composed mainly of quartz. Assuming they both came from the original erosion of the same rock, explain why quartz has survived to form sandstone G, whereas feldspar has not. So this is the very important point with sedimentary transportation. The quartz survives transport, whereas feldspar is broken down quickly. So quartz is harder and feldspar is softer. Quartz has no cleavage and feldspar has cleavage. So that means feldspar is more susceptible to physical attack, to breaking down by erosion and weathering. Quartz resists erosion, and also quartz is impervious, is resistant to chemical breakdown, whereas feldspar is broken down into clay minerals. So as you said there, feldspar undergoes chemical breakdown, hydrolysis to form those clay minerals. So which ones do you think they are? I think they're fairly obvious. Sandstone G has to be orthoquartzite, normally found in hot desert conditions, and sandstone H, the high percentage of feldspar, must make it an arkose. Looking at this, sometimes it's a question of elimination. Metaquartzite, in fact, is a metamorphic rock formed by the metamorphosis of orthoquartzite. Breccia, remember, is large angular fragments. Okay, this is from 2016. Again, take a bit of time to have a look at this question. Notice straight away, fine-grained clay matrix. It's a sandstone. What do you think that's going to be? So, from our mineral data sheet, we know that 1 was orthoclase feldspar, and mineral 2, which is colourless with no cleavage, has to be quartz. Describe the texture of the sandstone. Again, you should be familiar straight away with these type of answers. So what type of sandstone is it? Well, again, a metaquartzite is, in fact, a metamorphic rock, so it can't be that. We can rule out conglomerate because the class are angular, and look at the size again, 5 millimeters. That's quite small, so that's less than a centimeter. Breccia, for the same reason, it's too small. Orthoquartzite, we know, are rounded quartz particles, equigranular, so therefore it has to be Greywacke. Again, an extension question. So using evidence from sedimentary structures, the environment of deposition of a bed can be interpreted. For one sedimentary structure which can be used to interpret the environment of deposition, describe its appearance, explain how it can be used to interpret the environment of deposition. Notice underneath it talks about specific reference to fieldwork. If you can get some of our fieldwork in, fantastic. And really importantly, get a labelled diagram in. You can only get a maximum of 4 out of 6, however good your answer, if you don't get a labelled diagram. So what do we mean by sedimentary structures? Well, the sedimentary structures we've studied are graded bedding, which I'll go through in a second. Mud cracks, remember those desiccation cracks, which can show the right way up. Flute casts on the surface, which show paleocurrent, the direction of the original current. Cross-bedding, often common in orthoquartzite sandstones, show the direction of wind, and ripple marks as well. So any one of those could tell you about the environment of deposition. So let's look at graded bedding as that was in the video. First of all, as I said, draw a diagram. Remember, make sure you show the larger class at the base and the smaller class at the top. So describe it. So a graded bed shows fining. The class gets smaller from the base to the top of the structure. Class are coarser at the base, and it can be classed as poorly sorted. So with that diagram and that description, we've got 2 to 3 out of 6 already. But what about the next bit? How can that graded bed be used to interpret the environment of deposition? So we have to say what a graded bed, how it's caused. It's caused by the rapid deposition of a turbidity current. These are submarine sediment currents that flow off continental shelves, as you saw from the last video. As the turbidity current settles on the seafloor, the coarsest class is deposited first, then successive lighter particles are deposited on top of the larger class. It often forms muddy sandstones called Greywacke.